So let's take a moment and summarize where we are. Uh, I only have three problems left to do for distributed loads, shear and bending moment. Uh, so the next problem I'm going to throw at you is me throwing the kitchen sink. This is, if you can follow the next problem, you can do any of them. They'll be easy for you. This is the hardest thing I can basically throw at you. And we'll have some integration that we'll take a look at. I will not give you anything like this on an exam, but it's sort of an ultimate problem, and if this makes sense to you, you are ready. Okay. And I tend to do that. The last problem, sort of in a chapter, is generally the most intriguing, as it were. Now, then I'm going to be preparing you for exams. Okay. So the next two problems that I do after that, I'm going out of teaching mode into more of exam prep mode. So I'm going to have two problems off of former exams. Now let me just comment. I've never had one of these problems blow up on me, where I give a problem and the students mysteriously don't do well. These always go well on the exam. Students can base because we have a process by which you get to check your work. Okay. So, and you're going to find as we go through the two exam problems, they're kind of all the same. I just changed the beam or the shaft. That's all it is. They're all the same thing. Draw the shear and bending moment over the length of the shaft or beam, and tell me where the bending moment is maximized. Boom, done. You know, print. Go for coffee. So we're going to have two problems where you can see past exam problems, and then we will move on to our next chapter. So three to go. Here's my kind of me throwing everything at you. So what I have here is, if you look here, we have a cantilever beam coming out of here's the wall, here's the cantilever beam, 12-meter beam, and here's the hook here. I'm pinned to the end of this beam is another beam that makes its way over to dry land here, 6 meters away. And so the second beam has a distributed load, starts high, goes off to zero. Okay, so we need to do the shear and bending moment all the way across this thing. All right, so we got to do our supports first, as we would always do. And so when you go to do the supports, it's you take the wall away. Now, when you have a cantilever beam, what I just advocate is just why don't you put the force and moment in as if it to to solve for the actual shear and bending moment. It just makes sense. All right. Well, the point I want to bring up is if you just look at this piece, I have put cantilever beams on exams, midterm and final. Just depends on the mood I'm in. And one of the mistakes that students will make if they're going to blow this problem is when they take the wall away, they only put in a force. Now that's appropriate if you have a pin, but a wall also exerts a torque to hold this thing up. Okay, this is not a pin support. This is the wall holding it up. It's bolted in, somehow secured to the wall. The wall will provide a counter torque to keep this thing up here. You have to include that bending moment. So when you have cantilever beams, don't forget that. This is not a pin joint. All right. So having said that, so this is a sort of an ultimate problem, but the process is the same. We're going to figure out our supports. So we have here's our free body diagram. And so I have two of them, one for this beam, one for that beam. Okay. Uh, so here in this first beam, I have my shear and bending moment, 800 meters. Here's the 700 Newton point load. And this beam here is going to push down on this one. All right, so that's FB coming in. And likewise, this beam is going to hold up this end of that one, so it's pushing up. These will be equal and opposite. Since we have a pin, it's frictionless. So there's no torque here. So since there can be no torque coming through the beam, that says the bending moment here has to be zero. All right. As we go through the math, will reinforce that. All right. So then here, this beam pushes this one up. Then you have this distributed load. So this is 200 times 6. That's 1200. Triangle divided by 2. That leaves us 600 newtons. 1/3 from the fat end, 2 meters, and then 4 meters to the final support. So these are our free body diagrams. Now we need to just to go analyze these things in the usual way. If you sum the moments here at B, you would then have 600 times 2, and that's clockwise, plus FC times 6. Uh, solve for that, you would get FC is 200 newtons. All right. And then FB, if this is 200, that's 600. It's pretty obvious this one is 400. So put a 400 in here. So if I have 700 and 400 going down, then that V0 does go up, and it's 1100 newtons. So we have our initial shear. Okay. Last piece. So now we have to, if we sum the moments right here at A, or it says O, I'm going to have a coordinate system that starts X. So this will be X is 0 here. So you can call it A, you can call it O, I don't care. Summing the moments here. MB is clockwise, so minus MB, minus 700 times 8, and then here's 400 coming down, times 12. Solve for this, come up with minus 10,400 foot-pounds. All right? So we have our initial shear and bending moment. Okay, now next step is we would analyze our ends. All right, we have an end here, we have an end there. So looking at this would be x equals 12 to get to this spot. So if I look just at this beam, look on this beam, the right end of that beam, here's FB coming down. So then indeed, and this is 400. So indeed, we have 400 coming up. And since this is impossibly thin, there's nothing to generate a moment, we get a 0. And given the fact that we had a pin here, that makes complete sense. That should be 0 going across. If I go to the end, here's the free body diagram. FC was 200 coming up, so V is minus 200 going down. All right. There's nothing to generate a moment in here, and so the moment here at 18 is 0. All right. So we're ready to start taking a look at our plots, developing that, and we'll do this in the moderately usual way. So we're at, so initially, shear starts at 1100. If you look, bam, I'm at 1100. At 12 meters, 400. Boom, 12 meters, 400 on the shear. And then here we are, minus 200 over here. Bending moment starts at minus 10,400. I got that point. Makes its way to 0, and then here's another one at 0. All right. Let us walk the beam. So we walk across here, and we have 8 meters where nothing happens. So shear is at 1100. It will stay there. So put in a little construction line for myself. And there we have the first line. So as we walk across and look at force, let's bring this down a tad, we have a point force of 700 newtons. Go through 700 newtons, drop 700 newtons. That'll take us to 400 right here. Darken this one up a bit. And bam, we have that one in there. Now we go 4 meters and nothing happens. So we maintain where we are. Boom. Then at the pin, 400 down translates to 400 up. So we're on to the other system. And what's going to happen? There's a lot of force here. There's no force there, the distributed load. So this is going to start with a strong uh, slope, and then it's going to flatten out to zero slope. We're going to lose 600 newtons because this was 200 times 6 divided by 2. So that's 600 newtons net to lose. We're at 400. We got to drop to 200, so we're going to make it. And we're going to do something like that. And the big question is where does that happen? And the only way to figure that out is calculus. We'll get to that in a bit. All right, so we're at minus 10,400, minus 10,400, writing that in. And so now we have this piece, 1,100 times 8. Well, that'll add on 8,800, right? So that leaves us, here, let's go to 8. And right about here, this will be minus 1,600. So we're just going to jump up, boom, there we are. Okay, now we have 400 over 4 meters. Well, that's 1,600. Boom, that took us right to 0. So that first beam we've knocked off. All right. So from this point, now it's kind of a mystery. It's basically going to look something like the following. It's going to come up. Now I put that at this point. It's going to come up some amount, and then it's going to go do that. All right. So, and if you look at my drawing, so we know this is supposed to come up and come down. Looking at this, it looks like there's more area here than there. They should be equal. But this is just artistic license. All right. I'm not terribly concerned about that. And in fact, I would note that in terms of how I drew this, let's see, here's 12, 13, 14. This actually should be more like this. So this point here is going to work out to 14.5, and I actually drew it at 13.5. So it's a little off. But if you're just doing a sketch, more accurate, get a computer, all right? So we know roughly what this looks like. So here's what I want to do is let's get equations for this so that you could actually have a computer plot it for you. How would you do the equations for this? That's the next part of this problem. All right. So we're going to go to our next page here. And so we know that as we went into this thing, here was FB, our shear here was 400. And we had that right down there. All right. And our initial bending moment is 0. All right. So what we need to do is here was our point slope equation. So the initial shear, slope, and at the initial x position. All right. So our point that we started from right here, we are at, look where we are, 12 meters out, 200 Newton per meter distributed load. Okay, so put that into an equation. Well, very simple. So we go, where's our first point? So we have omega minus 200 equals, okay, slope. What's the slope here? The rise is 200, the run is 6, but it's running down, so that's negative slope. So that's going to be minus 200 over 6. And let's see, x minus, well, our point was at 12, x minus 12. So we have an equation for omega. Now we just need to move this to the other side, so we'll just jump up a tad. And let's make this picture bigger, easier for you to follow. There. So if I raise this up, we have the distributed load is 200 minus 200 over 6, x minus 12. And this is only valid here for x greater than 12. Okay. Well, once we have that, this is just this equation. So our initial condition was 400. Toss it in. Now the distributed load is going down. So that's what that negative is for. Now we just substitute our equation for that. So we're going from 12 to x, put in a bracket, 200 minus 200 over 6, x minus 12, bracket dx. And notice we have, so this term, that'll become a negative, and negative, negative, that'll become a positive, which makes sense because two wrongs always make a right. All right. So we need to integrate this thing. Well, that's very easily done. We have 400 minus 200, x minus 12. You should be able to do this without even thinking. And then we have a 200 over 6 and x minus 12 squared over 2. And there it is. All right. Let's move on to do this one. Our initial condition on the bending moment, we had over here 0. All right, no problem. So we have a 0. Now we simply take this term, bring it down. Integral 12 to x, 400 minus 200, x minus 12, plus, I must bring that 2 over, 200 over 12, x minus 12 squared. We'll bracket this all and put in a dx. All right. Now it's just a straight integration. We're left with 400 x minus 12 minus 200 x minus 12 squared over 2 plus 200. Now this is over 12, but this is going to become x minus 12 cubed over 3. So I'll bring the 3 down here, and that creates a 36 x minus 12 cubed. And there we have it. Now, I will note that if you go into this equation, MB of 18, if you put an 18 into there, you will get a 0, which is our end condition. So that's our check that we've done things correctly. Now, what we want to do, the key in this problem here, let's get the plot back. If you wanted to do this accurately, the question you would ask is where does this cross? Because that'll be the peak, and what is the peak value? All right, to get the peak, you would have to use this equation. Here, let's just bring that in. So you would simply have to say 400 minus 200 x minus 12 plus 200 on 6 x minus, oops, that's 12. 200 on 12 x minus 12 squared equals 0. All right, this is a quadratic. You can solve it a number of ways. I will leave that for you to do. If you do this, you will find this is zeroed out at x equals, find the number here, 14.535. Shear of 14.535 is 0. All right? So now to get the max, you would take this and substitute it into there. I'll let you do that. But I will tell you that the bending moment at this point works out to be 461.9 foot-pounds. So on this, if someone were to ask you in this problem, tell us where the bending moment is maximized. It is at 14.535 meters, about a meter out from where I actually did it in my sketch. And then this piece right here is 461.9 up. And that is the end of this problem. 2 more problems to do. Those are past exam problems. We'll see you soon.